Hi everybody and welcome back to Geology 109. This is the introduction to lab number 2 where we will be covering sediments and sedimentary rocks. Now the diagram that I have on this slide shows a number of different depositional environments, and this is not by any means an exhaustive list, but notice just where the reef is, or a delta, swamp, beach, stream, lake, and so on. These are all places today that we will find plants and animals and various different types of sediment. Now, millions of years from now, when the surface of the Earth has continued to change, as it does, there'll be a record of many of these environments preserved as sedimentary rocks. So anywhere today where sediment can accumulate, we call a depositional environment, and those will later be preserved into the geologic record in the form of sedimentary rocks. Last week we looked at minerals, igneous and metamorphic rocks, and we talked about texture and composition being important for identifying those, and with sedimentary rocks it's the same thing. We have different terms for texture and composition, of course, for sedimentary rocks than we do for igneous and metamorphic, but let's think about what each of these rocks mean. Igneous rocks, we talked about the difference of texture and composition because that would tell us something about the chemistry of a magma and how that igneous rock cooled. It tells us a story of the history of how we went from magma or lava to a rock. The different types of metamorphic rocks we looked at told us a story about the history of regional deformation, mountain building events, old rocks being heated and squeezed and transformed into something new. Sedimentary rocks represent ancient environments. These are ancient environments from the Earth's surface that are now preserved as rocks. And by learning about the texture and composition and some of the terms we use to describe sediments, we can interpret ancient environments just by looking at a sedimentary rock. So let's get started on reviewing sediments and sedimentary rocks in preparation for the lab this week. Our first part of the lab this week is going to be looking at the nature of sediments. So what exactly is a sediment? Well, we define a sediment as any unconsolidated material that is accumulated at the Earth's surface. These can be composed of fragmentary particles of pre-existing rocks and minerals. In this case, we call them clasts. So if you have a sediment, i.e. unconsolidated material that's accumulating at the Earth's surface, and it came from breaking pieces off of previously existing rocks and minerals, we would call those clasts. Another type of sediment, though, is what we call a chemical precipitant. And this isn't breaking a piece off, this is more chemically dissolving a piece of rock or mineral into a solution like water, and that water solution will flow to some new area, and then we reprecipitate our chemical sediments. So one is chemically altering the material and the other is physically damaging it. So we describe clasts usually, this doesn't really work too much in regards to chemical sediments, but we'll come back to that. We describe sediments in terms of texture, shape, and composition. By texture, we're referring to the grain size of the sedimentary rock, not an entire rock, but the individual components that make it up. We also describe sediments in terms of their shape, their geometric form. And in many cases, this is just as simple as is it rounded or angular or somewhere in between. And of course, we do need to pay attention to the composition of our sediments. What are they made of? What is the mineralogy of the sediment or that rock? Now, when we put all of this information together, it allows us to make some interpretations about sediments and sedimentary rocks. And these are important for interpreting the origin source, the original source of that sediment itself. What type of rock did this come from? It also helps us interpret the nature of the weathering processes of that source rock. Did it break physically or did it break chemically? We can learn something about how that sediment was moved around, its transport agent. Was it blown around in wind? Was it transported in water? Or was it transported in ice? We can get an idea of the duration of transport. How long was it moving, both in terms of time and how far in terms of distance? And finally, we can put all of this together in and of itself and describe sediment in terms of physical, chemical, and biological environments that are represented. And the word we use for that is facies, something that'll come up in the upcoming weeks in lecture. Well, how do we weather and break down sedimentary rocks and move them around to begin with? Weathering is the process in which we break pre-existing rocks down into sediment, whether it's clastic or chemical. Mechanical weathering and chemical weathering are these two main processes. Mechanical weathering is the physical breaking of pre-existing rocks and minerals to produce clastic sediments. Chemical weathering includes the chemical breakdown and incorporation of that material into a solution. Now, when we are dealing with mechanical weathering and clastic sediments, we classify those sediments predominantly based on size, using the Wentworth scale, as you can see here in Table 1. So a gravel class sediment would be anything from about 4 to 256 millimeters, and we can subdivide that class into names like pebble, cobble, and boulder. Sand is, you could have fine, medium, and coarse sand, anywhere from about 0.062 millimeters up to about 1 millimeter, and then muds are anything smaller than that. We get into our silts and clays. These are going to be very important for how we interpret how sediment moves around. The size of the grain is very, very important. And I want to remind you, we're not talking about the size of a hand sample of sedimentary rock. We're talking about the sediments that make up a piece of rock. Now, erosion is the transport of weathering products. Whether you are looking at chemical sediments or clastic particles, we are moving them from one location to the next, and that is erosion. Now, one important aspect of chemical weathering is how much or how well a rock is weathered largely depends on the minerals being weathered themselves. So if we look at the Goldich stability series here in Figure 1, you can see that quartz is kind of at the top of our pyramid, and this corresponds to being a very stable mineral. So mostly silica, most covalent bonds. In other words, it's really hard to chemically break down quartz. Can be done, it's just not done very easily. Muscovite and potassium feldspar are also on the higher end of stability. As we move down both sides of that stability series, though, notice down towards the bottom we have our calcium-rich plagioclase feldspars and our olivines and pyroxenes. These will chemically weather much quicker and much easier than things like quartz, muscovite, and potassium feldspar. As such, if you start out with a igneous rock, let's say granite, which has quartz, some muscovite, some potassium feldspar, and some other accessory minerals as well, and you start chemically weathering that, you will see some of those lower stability series minerals chemically break down and get washed away in solution. What you're left behind with then are the more stable, durable minerals that are harder to chemically weather. Now, if we look back at our clastic sediments, though, erosion and transport can greatly change characteristics of clastic sediments. We've already mentioned the Wentworth scale with size. You can start out with a large clast and break it down into smaller ones. But shape and sorting are also very important things to note when you're looking at sediments and sedimentary rocks, especially clastics. So if you were to be looking at a clastic sedimentary rock, you'd want to take note of the rough average size of most of the grains. You'd also want to describe their shape. When a sediment or a clast breaks off of a pre-existing rock, its initial shape is pretty jagged and angular. Think of it like a crumb if you were to break a cookie in half. Now, angular grains indicate that this is a relatively fresh clast, or it broke off of its source rock and then was immediately deposited. The longer that a clast is transported, both long in terms of duration and time, the more rounded it becomes. It tumbles downstream for thousands of years, and those sharp angular edges become broken down themselves, leaving you with a relatively rounded or a very well-rounded clast. So when you're again looking at a sedimentary rock, take note of the size of the clasts and the general shape of the clasts. Are they rounded, sub-rounded, subangular, or angular? And then you want to put those two together and describe the sorting of the sedimentary rock. So we have all these clasts and particles within it, and how well are those sizes and shapes sorted? Does this sedimentary rock have pretty uniform size and shape clasts, or is it mixed up all over? The photograph you see in the lower right of the screen is a glacial deposit. This is glacial debris, and notice we have big clasts and we have very, very fine grained clasts. Some of them are angular, some of them are rounded. We would describe this as poorly sorted. Now, most of the quartz sandstones that you'll look at in lab are very well sorted. When we have rounded grains that are well sorted and we have durable minerals left, we talk about the maturity of that body of sediment. So if you have predominantly quartz and maybe some potassium feldspar grains, and they're all well rounded and the rock is well sorted, we would say that's a mature sedimentary rock. Or if you're looking at a sedimentary rock like a greywacke, where you have different sizes of clasts and different compositions and different shapes, some rounded, some angular, we would say that is texturally and compositionally immature. But let's go back to erosion, transport, and deposition for a moment. We have these three different areas that a clastic sediment can be in. It can be eroding or being moved and breaking down from its source. It can be actively transported, and then it becomes deposited. Now, where do we draw the line for this? In figure 2 on the screen and in your lab printout, you'll notice that at the bottom of this we have our particle size in millimeters. So clay, silt, sand, gravel, and then larger gravels like pebbles, cobbles, and boulders, going from 0.001 to 1,000 millimeters in diameter. And then up the y-axis we have flow velocity in centimeters per second. Now, take note that clays and silts require a very high velocity of about 500 centimeters per second to actually erode. And that's because clays and silts have a sticky attractiveness. They have what we call high cohesion. Think about if you ever get mud on your shoe, it doesn't just fall off, it sticks to it. So we actually need to hit clays and silts with a high velocity, a high energy or flow velocity in order to disperse those clays. And once they do, they kind of start behaving like everything else, where the larger the clast, the higher energy it's needed to erode it and transport it. But once it falls below that transport threshold, we go towards deposition. So really, when a sediment has been deposited, that tells you there's been a change in the transportation of that grain. So if we had, for the sake of discussion, a grain that was, let's see here, let's say a good sand-sized particle, and let's say it was, so we're looking at maybe something like this, okay, like a 1 millimeter wide sand-sized particle. Okay. If we follow that up the y-axis, at actually at about 50, if we look at right about halfway, at about 50 centimeters per second of flow velocity, let's say a river is moving that fast, it will actually erode and pick up that grain of sand. Now the velocity can go down a little bit because now there's some momentum behind that grain as it's tumbling downstream. And as long as the velocity stays within this zone for that clast, it's going to stay moving. So just below 50, but it looks like above 10. If it falls below 10 centimeters per second, we end up here. And that is where we're going to start seeing it fall out of suspension and deposit somewhere. Now, if we were looking at something larger, like a 100 millimeter in diameter pebble or cobble, we actually need a much higher velocity to entrain it, to pick it up. And it still has a very narrow transport window, and then anything below about 500, it's going to start falling out of suspension. So it's important to take note of the size of the clasts you're looking at because it can tell you something about the velocity of the wind or water that at one point moved it. Now, once we've deposited sediment, we can start forming what are called sedimentary structures. These are the ways in which sediment grains, clasts, are actually deposited and the type of structures that they form. In some cases, in many cases, it's just what we call planar bedding. And that's what you're seeing both in the Badlands image outcrop and the close-up of these very thin layers of sediment in this shale, this sedimentary rock. This happens with pretty regular deposition of sediment let's see, in a quiet lake or a pond, you'll get this very fine-grained deposition of sediment. We're not dealing with large clasts. This is if you had a body of water that was kind of saturated with clay and it got very quiet and there wasn't a lot of movement, little by little those clay particles will start falling out of suspension and they'd start depositing at the bottom of that lake bed. And so sometimes we just get planar bedding like this, or very thin bedding plains. And these are very common in some of our shales. However, if there's some kind of current direction, whether it be wind or water, that is causing water or wind to blow in a certain direction, sediments that are falling out of suspension can also reflect that as well. Notice the herringbone-like structures that you see in these sandstones. These are what we call crossbeds. And if you look, we have sand stacked up in these angular beds, and then it is truncated and flattened on top. And then we have them dipping in a different direction, and then those are truncated on top. In between each one of those horizontal lines, where you see that tilting herringbone structure, that's telling you the direction in which the wind or water was moving when this sand was being deposited. Now, we don't have to guess at this because this is exactly how sediments are stacked up today. If you go to a desert and look at how a dune forms right in front of your eyes, this is the way that those form. And if you even go to a river basin and you look at some of the dunes that you might see around a beach, or the way that sand piles up on a point bar, you can also get these similar kind of sedimentary structures, these crossbeds. So crossbeds indicate a change in the direction of deposition or of current flow over a period of time. Now, since we're on the topic of sediment stacking up during deposition, I want to talk a little bit about ripple marks. If you go to a beach, or you go to a desert, or even go to a riverbed, you're probably going to encounter modern-day ripple marks. These are formed from a current direction stacking up sand, usually sand, but sometimes silt, in certain orientations. Now, if you take a ripple mark and you look at it in cross-section, there's a couple of things you might know. Some ripples are symmetrical, like the ones here in figure C. You can cut a line right down the middle and they're symmetrical. And then you have ripple marks like you see with figure B, where they are asymmetrical. They're kind of slanted. There isn't a perfectly symmetrical plane there. Our lower ripples that are symmetrical are called oscillation ripples. And these form from a current direction that goes back and forth, back and forth. And these are what you see with coastlines. The ripples that you see at the beach are formed from this. They're being formed perpendicular to the direction of the wave action that's crashing into the beach and going back and forth. So as the waves come in and go out, they stack up sand in one direction and then stack it up in the other way, producing these symmetrical oscillation ripples. However, if you go to a desert or you go to a riverbed and look at the types of ripples there, they're asymmetrical. They kind of tilt in one direction, and that's the steep direction is the direction in which the current is flowing. And this is because with a single direction of current, the sand gets kind of stacked up in one orientation and it stays that way. There's no opposite current to kind of balance things out. So if you're looking at a chunk of sandstone from 100 million years ago and you see ripple marks in it, you've got essentially three main options as to what kind of environment that sandstone and ripple marks are representing. And if you look very carefully at whether those ripples are symmetrical or not, it can help you out greatly. Now, there's a couple other sedimentary structures that I want to talk about that are pretty unique. One of them is called graded bedding. And in this case, you'll have a few centimeters of sedimentary rock. And if you look at it in side view, you'll see that there's really coarse material at the bottom. It gets progressively finer. And then it starts all over with new coarse material and gets progressively finer. So there's grading of grain size in clasts in these rocks. And these are formed from underwater turbidity flows. So you'll have a bunch of sediment that piles up on the continental shelf. It all goes cascading down at once, and it's like an underwater landslide. And then you'll get repeating sequences of this over and over again. They're sometimes called Buma sequences or turbidites or turbidity flows. So these indicate deep water environments. You might also see what we have down here in figure 12, mud cracks. Today, if you go walking around parts of the desert, maybe there'll be a seasonal lake that'll appear during the very narrow wet season that forms. When that happens, the clays that are in that sediment are going to absorb a lot of the water and they expand. However, during the dry season, when the water evaporates, the clays shrink, and then you get these polygonal-shaped mud crack tablets that start to form. Now, if another body of sediment fills in on top of these, it'll preserve those mud cracks. So mud cracks can also be found in areas like coastal environments during tidal areas. They can be found in playa lakes and a number of other places that go through extreme wet and dry cycles. So in this case, looking at the sedimentary structures of the mud cracks tell you what kind of environment you were looking at. It was arid to semi-arid with a narrow wet season, or you're looking at a tidal environment. So we've discussed how sediments are formed and how they move around, and we're focusing mostly on clasts at this point. But what about when they deposit, and let's say they formed in a number of these sedimentary structures? How do we actually turn these things into rocks once we have a bunch of pieces that have consolidated? Well, how do we go from sediment to sedimentary rocks? And this is done through processes known as diagenesis and lithification. Diagenesis and lithification is essentially turning sediment into stone. So you go from loose material to very, very hard, dense material. So we start with deposition, where we've deposited a bunch of clasts have either dropped or settled out. They're still loose, but during lithification, we're going to turn this into a rock, and that can happen in two different ways. First, you can have compaction. Compaction is no different than if you had mud in your hand, and you made a fist, and opened up your hand, and there was a ball of mud now in your palm. Essentially what you've done is you have rearranged those clasts, and you have forced water out of it, and so you've compacted them together. The other type of lithification is called cementation, and in this case, groundwater moves in between those loose grains and deposits dissolved minerals that will kind of glue or cement these grains together. The cement that we see with our sedimentary rocks is not always easy to determine. It's usually either silica or calcite. And if it's that way, you can easily tell the difference because the cement will react with acid, mild high HCl, if it's calcite, and it won't if it's silica. But there are some other minerals that can form cement, such as hematite. But either way, these are the two main ways in which we take loose sediment and turn it into a sedimentary rock. Now, so far we've been focusing on clastic sedimentary rocks, but I do want to mention a few things about our chemical precipitants, our chemical sediments and chemical sedimentary rocks. I want you to imagine you take a glass of water and you take a couple spoonfuls of salt and you put it into that water and you stir it up. If you stir it up enough, what happens to the grains? They disappear. Not really. What they're really doing is they're dissolving into solution into that water. Now, that water can flow to some other area, and if it becomes warm enough and it evaporates, or if you keep adding salt to it, eventually the salt crystals will start to form again into solids, and we call that precipitation. So chemical sedimentary rocks aren't formed the same way that clastic sedimentary rocks are. You know, a sandstone or a conglomerate forms from actually dropping sediment, and then it piles up and it compacts or cements. Chemical sedimentary rocks form in place. They grow in place, microcrystalline structures growing in place from an oversaturation and evaporation of that fluid. So in this example of the diagram that you can see here, we have water with a bunch of dissolved minerals in it. These have dissolved from previously existing rocks and minerals. Okay? As evaporation starts happening, we start seeing some crystals form and settle at the bottom. The more evaporation, the more crystalline growth we get, and then eventually the water is entirely gone. Our hypothetical lake here is evaporated, and we have all of these evaporite or chemical precipitants that are all stuck together. This is how we form rock salt. This is how we form gypsum. It's also how we form all of our carbonate sedimentary rocks like limestones and dollostones, and their various kind of subcategories of those types of rocks. If the chemical sedimentary rock is made of calcium carbonate, or essentially calcite, it will react with acid, and right away then you know you're dealing with a carbonate rock. However, not all chemical sedimentary rocks react with acid because not all of them are made of carbonate. Gypsum, chert, and halite will not react with acid because they're not calcium carbonate, but they also still are not formed from a whole bunch of pieces of things getting stuck together. All of these rocks grow through chemical precipitation. So how do we identify and classify sedimentary rocks? The first thing you want to do when you pick up a sample of sedimentary rock is determine the texture. You may need to look at the surface with a hand lens or a little microscope, and these will be supplied in lab. If you suspect that the rock might be chemical and might be carbonate, drop a very small amount of mild HCl on the surface. You don't need to hose it down, just a drop will do, and see if it reacts. It'll fizz like mixing vinegar and baking soda. If the rock does not react, it could still be a chemical sedimentary rock, or it could be clastic. If you can see visible fragments that aren't necessarily fossils, then you're dealing with a clastic, or sometimes called detrital sedimentary rock. If it has a sandy or gritty feel to it, if it is finer than sand but it feels kind of chalky, these are all ways of indicating that your rock is clastic. If it's finer than sand and it has a layered texture to it and it's sedimentary, it's probably clastic. A rock would be chemical or biochemical if it's mostly made of fossil shells. If you can see interlocking crystals, if it's microcrystalline, it's very smooth but it has a conchoidal fracture. If you have clasts that aren't shell fragments, or if it's fine grained and it reacts with acid, or it has little tiny beads which we call ooids, these would be signs of chemical sedimentary rocks. So when you pick up a sample of sedimentary rock, the first thing you should look for is, do I see pieces of things in this? Is this made of clasts? If it is, you want to go down the clastic classification system. If it's not, start running some tests and see if it might be chemical. Now, in your lab printout, you have a couple of tables. Table 2 is the way that we classify rocks using sedimentary parameters. And then table 3 tells you where some of these rocks originated. So here's table 2. These are our sedimentary rock analysis and classification. Notice the top half is clastic or detrital. And in this case, the composition of the rock is going to be mostly quartz with some lesser amounts of feldspar and some rock fragments or clay minerals. If you have gravel-sized particles larger than 2 millimeters, and they're generally poorly sorted, look at the shape of the rock fragments then. If they're rounded, it's a conglomerate. If they're angular, it's a breccia. If your rock is fissile, which means it splits into very, very thin sheets, it's probably a shale or a mudstone. Alternatively, if you find that your rock does react with hydrochloric acid, then it is not only chemical, but it's a carbonate rock, in which case it could be chalk, one of the various types of limestones, coquinas, or microcrystalline micrites. If it doesn't react with acid, but it is crystalline, it could be diatomite or chert if it's made of silica, peat or coal if it's pure carbon, or rock salt or gypsum if it's an evaporite. Now, where do these come from, though? Table 3 is showing you different sedimentary environments. Conglomerates and quartz sandstones are typically indicative of river or stream channels. Shales can be parts of rivers, and they can also be parts of floodplains. Breccias and arkoses are commonly found in alluvial fans. Sandstones can form in lakes, they can form in desert or coastal dunes, a wide variety of places. And we also jump down then towards our chemical sedimentary rocks. Notice that a lot of these are marine. So our limestones, chalks, coquinas, and so on usually form in marine environments, deeper water environments. So there's a relationship between why we want to understand sedimentary rocks, because we can learn about different types of environments from Earth's past. So for lab exercise 2, you want to read through the entire lab exercise that's available on Canvas. You obviously want to watch the video that you are just about to be finished watching. You want to complete pre-lab 2, just to kind of let me know that you're coming prepared. And then when you get into class, we're going to start by doing exercise 2A, which is looking at properties of known sedimentary rocks and structures. 2B is going to involve identifying a number of unknown sedimentary rock samples. Now, when you look at the form for the lab printout and where you'll be putting this information for part 2B, you won't be necessarily filling in every single cell of that table. What you want to do is run your tests and then see which sedimentary rock best fits those particular types of characteristics. Okay. Also, don't forget that lab exercise 1 is due before you come to class, and lab exercise 2 will be due within 1 week of it being assigned. All of these labs are due within 1 week of them being assigned. Also, keep in mind that next week we will have lab quiz 1, which will cover rocks and minerals, all of the ones that we've covered. And we'll also be doing lab exercise 3, which is an introduction to fossils. Both of these are going to be entirely online. The next time after this lab on sedimentary rocks, the next time we'll meet in person for lab will be week 5. So make sure you go through everything for lab very carefully before you arrive. Make sure you bring PPE. Make sure you show up at the correct time. And feel free to email me if you have any questions. Until then, we'll see you in lab.